This work is a joint work with SHIP Security, Huawei Canada, Microsoft Research, and UC Berkeley and Fudan University. Today we are going to talk about a web attack paper. We conducted a security analysis of a web protocol called CORS, Cross-Origin Resource Sharing, which is used to relax the default the same origin policy and enable cross-origin network access. And first, we look at the same origin policy. The same origin policy is the foundation for client-side web security, and it isolates resource from different origins. And under the same origin policy, client-side scripts can send requests to third-party servers, but they can't read the response. So, but with the development of web, many applications need the cross-origin reading permission. So developers have come up some workarounds, such as JSON-P, to serve the lead. But JSON-P have a lot of security issues. So cross-origin resource sharing is proposed to solve the problem of JSON-P, and it's a more disciplined mechanism and has been supported by all the browsers and has been adopted by mainstream websites. Today, our work is to conduct a security analysis of CORS protocol. And we found the design, implementation, and the deployment of CORS are subject to a number of security issues. For example, an attacker can use the CORS features to hack Intranet from outside, or remotely influence cookie presence on any website. We also conducted a large-scale measurement on popular websites and found 27% of websites have insecure CORS configurations. We also proposed some mitigations, and some of them have been adopted by web standard and major browsers. Today, in this talk, we first introduce CORS background, and then we detail CORS security issues, including browser-side issues and server-side issues. Then we present CORS deployment in the real world. Finally, we discuss mitigations. First, we look at the web background. The default same origin policy is too restrictive. It prevents cross-origin reading. So, but the developers need the cross-origin reading. So CORS is proposed to solve the problem. The core idea of CORS is very simple. First, the requesting website issue a cross-site request. And the browser, for each cross-site request, browser will automatically add an origin header to the request, indicate the requesting origin. And then the server returns the access control policy to indicate the allowed origins. Finally, the browser will check the requesting origin, whether the requested origin matches the allowed origin. Only if yes, the requesting website can read the response. Here's an example of CORS JavaScript interface. We can see that the CORS interface allows JavaScript to modify request method, headers, and bodies. And this interface is very powerful and may break CSF defense of many websites, because many websites use custom headers to defend the CSF attack. So CORS classify requests into two categories, simple requests and non-simple requests. A simple request must satisfy all the three conditions. First, the request method is head, get, or post, and the request headers are not customized, except line headers. And third, the content type header value is one of specific values. For simple requests, it is considered a safe request and it can be sent out directly by browser. For non-simple request, it's a lot covered in our talk. You can find the detail in the paper. We studied the course design and implementation, and we found many security issues. We first talk about the browser-side issues. Course allows the simple requests to be sent freely by default. But the scope of simple requests is in fact further relaxed sending permissions, allowing malicious customization of HTTP headers and bodies. And we found 4 types of attacks which exploiting these relaxed sending permissions. And here we only talk about first three of them. The first one is permissive header values. CORS allows JavaScript to modify 9 whitelist headers, but it imposes few limitations on header values. So that means an attacker can customize these headers with attacking payload. For example, the attacker can set the accept header to a shell shock vulnerability payload. We tested 5 major browsers and found 4 of them are affected, all except Safari are vulnerable. And of course, restricts content type header to 3 specific values. But we found this restriction can be bypassed due to implementation flaws. We tested 5 mainstream browsers and found all of them prefix match the 3 values. So an attacker can still craft content type header with malicious content by appending attacker payload to a valid value. We found this implementation flaw allows a web attacker to obtain a shell on Intranet server from outside by sending cross-origin requests from victim's browser and exploit Apache Struts vulnerability in the Intranet. Here is a demo video. On the left side is the victim's browser in the Intranet. On the right side is the attacker in the Internet. First, the attacker listens on the Internet server, and the Internet victim visits a malicious page, and the attacker has obtained a shell on the Intranet server. And the second problem is few limitations on header size. CORS allows JavaScript to modify headers, but it doesn't have a limitation on header size. We tested 5 major browsers and found all of them allow at least 16 megabytes header size, which is much larger than header size limitation of servers. We found that the difference header size limitation can be exploited by a web attacker to launch side channel attacks, remotely inferring a cookie presence on any website. Here is the attack, how this attack works. To carry out this attack, first the attacker measures the header size limitation of the target website by directly issuing requests to the target server and increasing the header size until receive 400 byte request response. And then the attacker send simple requests from victim's browser with crafted values and make sure the total header size is slightly smaller than the header size limitation of the target server. If a cookie is present in victim's browser, the cookie will automatically attach to the request. So the total size will exceed the target server limitation, and a 400 byte request response is returned. If cookie is not present, then the target server will return a 200 OK response. But here is a problem. There is a problem here. In fact, the attacker cannot directly observe whether a response code is 200 or 400. So the attacker needs to infer the response code through timing channel. One general timing channel is response time. If the attacker issue a simple request towards a large field, a 200 response is significantly slower than 400 response. And in Chrome, the performance.getEntries API directly exposes whether a request is successful or not. The presence of a cookie can leakage a lot of private information. For example, the attacker can remotely infer victims' health conditions by looking for visits to a particular disease or hospital website. The third issue is flexible body values. CORS allows JavaScript to customize request bodies, but doesn't have limitation on the values. So an attacker can craft any binary data in the request body. We found this ability enable attacker to exploit a binary protocol service. In this case, we found is Macos built-in Apple file server, AFP server. The attacker can craft a malicious request, making the header to be ignored by the AFP server, and constructing its binary body for communication with the AFP server. We tested 5 browsers, and all of them are affected. Here is a demo video to show how an attacker can create local files in victim's local file system only if a victim visits a malicious page. First, we can see that there is a low file in current folder, and then the victim visits a malicious page, and a cross-origin request is sent to FP server. And then we can say that a new file is created on a victim's local file system. Then we talk about server-side issues. We found 7 types of server-side issues. Here, we only talk about 3 of them. First, we look at how CORS policy works. For example, when B.com wants to share data with A.com, it can configure the CORS policy to be access control along A.com. But what if B.com also wants to share data with C.com? Maybe you want to specify a comma-separated list of origins. But actually, it's an invalid configuration. In CORS specification, the CORS policy can only be single origin or null or a wildcard. So that means that the web developer have to dynamically generate different CORS policies for different requesting origin. We found this dynamic generation process is error-prone in practice. The simplest way to generate a CORS policy is blindly reflect origin header. But we found this configuration is quite dangerous because it's equivalent to trusting any website. And we found, in our measurement, we found about 1 in 30 websites have made this mistake, including some important websites. And we also found some web developers attempt to validate requesting origin, but still made mistakes. Here is an example of Nginx configuration from Stack Overflow. The resource server tried to check whether the origin header matches example.com or foo.com, but it forgot the ending character, which resulted in trusting any domain's prefix with the trusted domain. Here is the example.com. So the attacker can use the example.com, evil.com to read the authenticated resource. We also found some important websites have this mistake. We found some other web applications check whether the origin header value ends with example.com. But this configuration is still available. It actually accepts any domain ending with example.com, including attack example.com, which can be rejected by attackers. And we found some websites, important websites also have this mistake. The third type of misconfiguration is HTTPS trusted HTTP. HTTPS is designed to secure communication over insecure network. So a man-in-the-middle attacker cannot directly read content on HTTPS website. However, if a HTTPS website is configured to trust the HTTP website, then the man-in-the-middle attacker can first hijack the HTTP website and then steal secrets on HTTPS website by sending cross-origin requests. And there are some websites also made this mistake. Finally, we want to understand the real-world impact of CORS misconfiguration problems. We conducted we target Alex top 50,000 websites and extract all of their subdomains from a passive DNS database. And for each subdomain, we actively probe CORS configurations. Totally, we found 400,000 subdomains are configured CORS, and about 27% of them have insecure configurations. These websites are very important websites, are popular websites because they are in the Alex top 30,000 websites. So CORS misconfiguration problem is widespread in current internet. We reported these problems to Web Standard Organization, working group, and had a discussion with the authors of CORS specification. They accepted some of our suggestions and made some changes to the specification. More specifically, they add more restrictions to CORS sample requests. They also acknowledged us in the CORS specification. And regarding the CORS misconfiguration issues, they suggest that the misconfigured websites should fix these issues by themselves without changing the specification. However, they agree to our suggestion to add a security consideration to summarize all the misconfiguration cases in the standard. We also reported this problem to browsers. Chrome and Firefox browser have released a patch to block the Apple file server port, AFP port, and are implementing the specification changes. And Safari is also testing these changes with a beta testing program. We also reported this problem to CORS frameworks. We found 10 out of 11 CORS frameworks have insecure CORS configurations. So there are many CORS frameworks is also available. and some of them have fixed this issue. We also provide an open source tool for web developers to identify course misconfiguration issues. Here's a screenshot of this tool. I strongly suggest web developers to check their websites whether have correct course configurations. Summary. We conducted an empirical study on CORS and discovered a lot of security issues. Some of them are not just the implementation flaws, but fundamental issues in browsers and specs. We also propose some mitigations, and some of them have been adopted by our standard and major browsers. And that's my talk. Thank you.
Very nice, solid work. I really like listening to it. So I have a question. So in the beginning, you talk about some client-side browser issues. Does those issues only exist in CORS, or it also exists in WebSocket?
A very good question. Yeah. But in this work, we only examined the CORS. We are not sure whether this problem exists with the WebSocket. Maybe, yeah, maybe. I haven't tried that. Yeah. Maybe that is a good research question. Maybe you can find that.
Jens Müller from Ruhr University Bochum. So I also think most of those client things are they're actually just normal JavaScript, nothing to do with CORS. And first of all, nice write-up. But all the 7 attacks you published, you probably remember James Kettle. He published them 2 years ago, all of them. And also, I think a large-scale evaluation of the Alexa million was done. I think we published them 1 year ago. So my question is, nice write-up, but what is actually new on your talk that hasn't been published before?
Sorry, I have difficulty in listening.
What is your major contribution that hasn't been published before?
What is the contribution to this paper? Okay. Yes. Some for misconfiguration issues, some web developers have found some issues, but there is a low empirical study, a comprehensive study on the CORS protocol, and we found some new security issues in browsers, and we also and it has been recognized by CORS specification and adopted by major browsers. I think,
Thank you.
Yeah.
Also, I guess that's a question for the reviewers, not the author. One question about the insecure configurations. So I've also looked into this at some point, and I saw that some sites will give you a reflected origin and access control credentials, true, but only if you're not logged in, and they send a different CORS header once you are logged in. Did you check those? Take a look at sites where you could log in and see if there's a difference between the CORS headers being delivered when you're not logged in versus when you are logged in?
Yeah. That's a good question. Yeah. But in our measurement, we only check the users are not logged in. Yeah. Maybe we can do more research on how to measurement the CORS configurations with the credentials.
It would be interesting to understand if there is a difference, because I found some sites that seemed to be vulnerable, and then you logged in and the CORS policy changed, it was no longer vulnerable.
Yeah, that's true. Yeah. It could happen. Yeah. But there are still many websites available. That doesn't change their CORS policy. Yeah.
Thank you.
Yeah.
Okay, let's thank the speaker again.